Okay, this is a recording of 6-3 for Tuesday 3/12, and we just had some homework check time and work time for 6.2. So I'm not sure that we'll get done with 6-3 today, but we'll try to put a good dent in it. So now we want to talk about direction angles, and then we talked about this part yesterday. I do want to just kind of put this back up here to talk about this. And so for a vector in component form, we said that's like, you know, since we put that unit vector on the coordinate axis, we can think of that as having the same values as a unit circle, and we have a lot of experience with that, and so that each point on that unit circle can be thought of as the cosine theta and sine theta, and so the component form of that is cosine theta sine theta, and if we put it in linear combination form, it's cosine theta I plus sine theta j. And remember, I and j are also vectors, so if we write them freehand, we have to have the little arrows over them. And usually I just put that way instead of the dots. Sometimes if I remember to do that. So one thing to kind of note to self, because we're also going to do some application problems, when we're talking in terms of just purely these vectors, we're talking about the angle having the initial side at the positive x-axis, correct? And so as we work a problem, we might have to then in the end kind of look at that. Also, I'm just going to forewarn you that when we find these angles, we're going to find a reference angle and then have to find the actual angle from that. So kind of putting together things that we've done before as we've gone through things. So then if you think about this vector in and vector u is that unit vector, and it has coordinates cosine theta, or it has coordinates is maybe the wrong word, but I can't think of the right word, is where the position decider, cosine theta, sine theta. So if that's the unit vector and we want to use any vector v, then does it make sense that that cosine theta, sine theta will give us the direction, and we can use the magnitude of v to find the length of that. And so this is a big formula for us, and so v in linear combination form, v is equal to AI plus BJ. Just a reminder, that is not the I square root of -1. We talked about that yesterday. And so now any vector v can be written as the magnitude of v times the cosine theta sine theta. And that is kind of the component version of that. And then the linear combination method or version is that vector v is the magnitude of v cosine theta times I plus the magnitude of v times the sine theta times j. And so that gives us kind of the pieces of this. And then I'm going to kind of remind you, and I'm going to do some color coding here. I'm going to remind you that this version right here, let's see, to be able to point out that, I'll use yellow. So this version is just vector v, plain old linear combination, correct? And this is also vector v in linear combination. Do you agree? So what does A equal? What does A equal in both of these? Because if it's a unit vector, A would be cosine theta. But if it's any vector v, what's A equal? the magnitude of v times cosine theta, and then b is the magnitude of v times the sine of theta. And so I did want to color code these, but I'm going to go back. And so what that means for us is that a right here is this stuff. Oops. I have to not include the I, remember, because the I kind of tells us that positioning. And the B part here is this piece of this. And so those A and B things are going to be important to us as we go through things. Now, when we think about this angle, and in the last picture we had that coordinate axis and the angle, when we think about an angle, we want to be able to find that angle, and here's the information we know. We know this A and B, which are the magnitude of V times cosine theta and the magnitude of V times sine theta. So I want to use a trig function that's going to help me kind of get that angle theta. So do you agree that in general the tangent theta is sine theta over cosine theta? Correct? And so if I know the sine of theta and the cosine of theta, I can figure out what the tangent of theta is. And do you agree that if I want to, I can multiply the numerator and the denominator by the same number, correct? And that won't change the value. What do you think I want to multiply the numerator and denominator by? Any thoughts? Well, look at what I boxed in red and green. They're not exactly the sine and the cosine, but they have that magnitude of V multiplied by each of them. So what I can do is I can say, well, the tangent theta is sine theta over cosine theta, but the tangent theta can also be thought of as the norm of, or excuse me, the magnitude of V over the magnitude of V, because that'll be 1 over 1, so it doesn't change the value, times, and I'll just kind of lengthen that, sine theta over cosine theta. And then what can I replace the magnitude of V times sine theta with from way over in the top left? What is the magnitude of V sine theta equal to? B. And what is the magnitude of V cosine theta equal to? A. So what that gives us is a very nice little ratio that says the tangent of theta is going to equal B over A. And I have those kind of written and color-coded. I can't kind of see them. Maybe I can just get them all on the slide at the same time. So I'll just kind of say, so B is right here, and this is B, and so this is equal to B, so I can replace it there, and then A is right here, and I can replace it with all of that, and then there's A. So without having to go through all this mess here, although I am going to need to know that version, if I have it in linear combination form, I should be able to just get that tangent theta is equal to B over A. Now, I'm going to caution you here as well that tangent of theta, the theta that you get, is a reference angle or related to the reference angle. It won't always give you the exact angle. So the theta here is either, a reference angle or because sometimes if you put in a negative, it's going to give you that inverse function. And the other dynamic is we're talking in degrees. So theoretically, when we do inverse trig functions, we're getting them in radians, but then we're going to convert them to degrees, but we're just going to get them in degrees, and then we'll be done. And I'll just say theta is going to be the reference angle or related to the reference angle. And it might be the actual angle, but I want you to always think of it as a reference angle, and then if it turns out to be the actual angle, you can just go kind of woohoo, and you don't have to worry about, the fact that whether that is going to be the case when it's not. Okay, so number 7, we're going to find the direction angle of each vector, and we'll do this first one together, and I'm just going to tell you, we're doing the easy one together, and then you'll do the one that's just a little harder. Not much, though. So when you write this 7a, remember, you have to write vector u is 3I plus 3j. And so those are all vectors, and really we can't write them in bold, so we do it like that. And so then this vector u, which is not a unit vector, just note to self, that notation we use is often used for u, a unit vector, or it can be any vector. But we know that's ai plus bj, and all we want is the direction. Just give me a head nod. If I asked for the magnitude, yes or no, could you give it to me? Yes or no, individually. Yes or no? The magnitude, yeah. Magnitude. The magnitude is the length, distance, Pythagorean theorem, right? Square root of 3 squared plus 3 squared. Okay, so just kind of a reminder, because I'm not asked for the direction and the magnitude, but on a test I might be, so I just want to remember that. And then I also want to remind you that I could plot this point, and this point would be plotted as 3, 3, and there would be my vector in kind of that standard position. So B is 3 and A is 3, and I wrote it like this because people aren't here, so they know which one is which. So that means for the reference angle, the tangent of theta is 3 over 3, so the tangent of theta is 1. When is the tangent of theta equal to 1? 45 degrees. And so we will be using degrees as we go this way. So our reference theta is 45 degrees. Well, actually, is that the actual angle direction as well? Yes. So in this case, we're in that first quadrant. The reference angle is the angle. And so the direction, and generally, because I use theta a lot of times as the reference angle, generally I'll just say the word direction then. Direction is 45 degrees. And for this one, I don't know. For this one, we know that it is just the same as that angle. So take a minute, do this one, see if you can get this one. And I'm going to tell you right now, this 45 was on the table of values. You know what I'm talking about, right? And this one is not. So you just have to use the calculator to get the inverse trig function. And I'm rounded to 2 decimal places. And so for this one, we'll just say 2 decimal places. And I'll give you a few minutes to do that. So 7b. Reference angle, now find. Oh, make sure, I'm just going to go back a minute. Yeah. Did you get this yet? This was right. Oh, think about plotting. Oh, by the way, I think you wrote the problem wrong. Um, yeah. Did you? Okay, so maybe you've heard me, kind of mumbling a little bit. I maybe could have paused it, but I did not. And so I've talked to a couple of people. Things to keep in mind is this vector in general form is I'll write it up here. The vector is AI plus BJ, and so then in this problem. Uh, B is -4 and A is 3. And so let's just see if I can find any of my work here. Or not. Um, oh, here's something. Here's something that I wrote down. And so let's see what it is. Oh yeah, this is my oh, I must have not, I don't know. So if I put my axis here and I kind of plot in my head this point 3, -4, which, is the component form of this vector. If I go out 3 and down 4, my scale isn't good, but I'm going to end up in this quadrant. Do you agree? And so when I get my angle theta, it's going to be the angle that's right there. And it's actually, if I put it in as -4/3, you don't really have to think about the SIGN, positive or negativeness, because you can kind of think about that reference angle. In this case, it will give us that correct reference angle, but sometimes it will not. And I thought maybe I could, oh, here we go. So if I don't touch right where my writing is, then I can't see it. And so let's see. I get the tangent theta is -4/3. That theta is going to be my reference angle. And so what is that reference angle? 53.13. And then how am I, if that angle is 53, and I think it gives you it as -53, right? Because tangent, if it's negative, which it is, it's going to give you in that fourth quadrant. If you put it in as positive, it'll give you in the first quadrant. Either way, you have to kind of just think in your head the actual 53 point whatever is 0.13 is the reference angle. And then how are you going to find the actual angle? 360 minus that. And so it gives you that negative, but you can ignore the negative for now. And we take 360 minus the 53.13. And so that gives us a direction of 306.87 degrees as we look at it. So now the next ones are going to be application problems. There's 3 application problems. I'm quite sure I won't get through all 3 of them today, but I do want to get a start on them so that we can kind of finish them up tomorrow. So I blocked some things out because for this slide, I just want you to look at it, and then we'll draw the picture in the next one. It says find the component form of the vector. So just note to self, that means my answer is going to be in component form at the very end. That represents the velocity of an airplane descending at a speed of 150 miles per hour. So the way we generally convert speed into distance is we say, well, how far would it go in 1 hour, right? And so we're going to say that this distance it's gone from there to there is 150 miles. And an angle of 20 degrees below horizontal as shown, which is a little odd way to put that. So I didn't block all of this out, but do you agree that this piece right here is 20 degrees, correct? But the actual angle that we're going to use is from the positive x-axis around to here. So what's that? 200. And so I actually have the picture is really the picture that they've drawn with those things labeled. But I know that sometimes I ask you to draw those pictures, so I wanted to give you access to that as well. So that's how they get that 200 degrees. And by the way, like, have we talked about this before, that airplanes go from kind of north and then degrees and not from north and clockwise? Yes or no? Okay, because we don't talk about that very often. Because ships go like the trig star surveying, north or south, and then east or west of there. But airplanes go kind of north and then clockwise around. So, you know, and then mathematically we were positive x-axis and then counterclockwise. So this is our picture as we're looking at that, and all we want to do is find the component form of the vector that represents this, and then we'll do one that, you know, maybe involves a little bit more action or something else happening. So for this one, really, we have to get that our magnitude is just going to be what? What's the length of that vector going to be? What are we counting it as? 150. And so, you know, 150 miles per hour, so we're just saying it's 150 in 1 hour. And what's our direction? Our direction is theta is 200 degrees. And so now we just want to know how to find that vector from that other page. So the vector is equal to the magnitude of v times what goes there? Cosine theta I plus the magnitude of v sine theta j. So we just plug them in and see what happens. So for this one, this is 150 cosine 200 degrees plus 150 sine 200 degrees. Oh, I forgot my I back here because I was a little worried about fitting this in. So I will erase this piece and I'll put my I right there. Just kidding. Plus 150 sine theta j. And, oh yes, yeah, thank you. And sine 200 degrees J. So do we agree that this reference angle is not going to be on that table of values, so we're just plugging things in? And so what we need is 150 cosine 200 degrees and then 150 sine 200 degrees, and we'll round it to 2 decimal places. Who can tell me what that one is? Negative 140.95 I. And then is it going to be, oh, it's going to be minus. Do you agree? Because, you know, it's negative, negative. Minus what? 51.30 j. And so this is vector v, and we're using really a linear combination form, right? But we were asked for the component form. That was on the last slide. So we're asked for the component form. What is the component form? Just the less than symbol, negative 140.95, comma, negative 51.30. And that is the component form of the answer. Now, just a little note to self. Suppose I'm taking a test and I want to feel confident that that is right. 2 things can help me feel confident. First, one thing is that I got a negative and a negative, and I know when I plot a negative and a negative, I'm in that 3rd quadrant, and that's what my picture looks like, right? So that tells me I'm kind of good. What else could I check with this to get something off of here, or something close, because it's rounded numbers? The Pythagorean theorem, right? So it's the magnitude. I can check the magnitude of that. And so check the magnitude and just see. So the square root of negative 140.95 in parentheses squared plus negative 51.30 squared should be approximately what? Right, which is approximately 150. So 149.995. And so that is a check. And of course, because those weren't exact values, it's not going to be the exact thing on there as we go either. So the next one is always a little bit harder for me, and this is a force problem. And so here is the picture. It says a force of 600 pounds is required to pull a boat and trailer up a ramp inclined at 15 degrees from horizontal. Find the combined weight of the boat and trailer. And so you might want to just take a moment and sketch these pictures. I'll sort of sketch them here as well. And so, you know, they've got right at the tire. I'm not going to draw all that, but they've got that point is B right there. And then this triangle, that's a right triangle, with C there and A there, and this 15 degrees is kind of a tipped and turned version, I guess is how I'm going to say that, of this triangle that would be 15 degrees there with W there. D is right here. That's a right angle. And did I miss any things labeling? I don't think so as I went. And of course my picture is not great. Now, the thing we know is, you know, and just like that miles per hour, this 600 pounds of force is required to pull the boat. Oh, and so let's think about where these vectors are. This vector, vector BA is pushing down. Do you agree? That's pushing down. We want to move the boat up the ramp. So vector AC is going, oops, from A towards C. I'll just kind of, I didn't do a great job there as we go. And then BC is also kind of pushing down on that as we go. And since we're trying to pull along really AC here, this boat up the ramp, we're going to call that the 600. I was going to say 400. I don't know. The force. We're going to put that like that as we go. Now, look at this little right triangle, and I'm going to retrace it in green just so that I can talk about it. So do you agree it's a right triangle? And the angle that's there is 15 degrees, and we know the opposite side, correct, is 600. And so we want the side that is BA, and then that's just the weight pushing straight down. And that's the what of that little green triangle? The hypotenuse. So when we're talking opposite side and hypotenuse, what trig function are we talking? Because it's a right triangle. Sine. So we know that the sine of 15 degrees is going to equal, and the way that I'm going to write that is in terms of vectors. The magnitude of vector AC over, because that's the opposite side, over the magnitude of vector BA. And then I'm going to put in what I know and figure out what that vector BA is, that combined weight of the boat and trailer. And so I'll plug in sine 15 degrees is equal to AC is 600 over the magnitude of BA. And then what's the magnitude of BA going to equal? 600, oops, over the sine of 15 degrees. So take a minute. Now it's just typing it in. And of course, we are using degrees in these. So just, you know, that if the other ones have worked out, you know you're using degrees. And this one will just go to the nearest whole number. What is it? 2,318 pounds. As we go. So the next one we're going to look at just the setup right now, and then kind of we'll go to it tomorrow as well. So look at this. An airplane is traveling at a speed of 500 miles per hour. So we're going to use a 1 hour time and say 500. And then its bearing is 330 degrees. So do you agree that plane is in the second quadrant, correct? Because we've talked about the fact that three planes bearing is from kind of that north and then clockwise around 300 at a fixed altitude with a negligible wind velocity as shown in the figure below on the left. When the airplane reaches a certain point, it encounters a wind. So this second vector is this little tiny vector. Do you agree that it's also tiny relatively speaking, correct? Because the wind is only 70 miles per hour, so in 1 hour it would move 70 miles, whereas the plane in 1 hour would move 500 miles. And so, but it is pushing that plane, and they do have to kind of think about that. And its direction, because wind is that north or south, and then east or west, it's going north 45 degrees east. So do you agree that's a first quadrant angle? Yes, as we look at it. And so then our job is to figure out what the resultant speed and direction of the plane are. And I'll put this to this next slide. And I put that 120 degrees in there. Oh, because I forgot to ask you about it. Darn. Well, now you know. I feel bad. So that's what I wanted to go over. So if that is 330 degrees, what do you have to do to get that angle? How do you, because so wait, what is this angle right there? 60 is this angle. And so this one is like from our standard position, 180 minus 60, so it's 120 degrees. Do you agree with that? Okay, and then here it is of 120. So to me, that was just a little bit of a jump, just saying its bearing is 330, and then boom, here's the picture. Do you know where that 120 comes from? Because you're going to have to know that. And then we'll talk about this one tomorrow, and that'll be the end of 6.3, and then we'll move on to vectors and dot products. Have you done dot products in a science? Huh? Never heard of them? Okay. Not in a math class, I didn't think, but sometimes in a science class, people have done them before us. Okay, so that is it for today. If you're gone, we'll see you tomorrow.